Hey everyone, thank you so much for watching Weaviate on YouTube. This video will dive into a new paper titled Retrieving Text Based on Abstract Descriptions. Quickly before getting into it, if you like these kind of paper summary videos, please let us know by hitting the like button and subscribing to the channel. Here's a quick overview of the paper in case you're in a hurry and don't want to hear the full experimental details. So this concept of retrieving text based on abstract descriptions, what drew me to this paper is its similarity to this concept of summary indexing. So summary indexing describes maybe at the chunk level. So for each text chunk, say you have full podcast clips or paragraphs of text, instead of just vectorizing that full podcast clip, you'd instead use, say, a large language model to write a summary of the text and then vectorize that summary of the text. We'll talk about how economical it is to use a large language model for this task, but that's kind of the general setup is, you summarize the full thing into how you write the summary, whether it's an abstract description that kind of blur out the specific details or just a summary of the information content, then vectorizing and indexing this content is quite an interesting idea. It's also very interesting for this concept of a top level index. So say your data is, podcasts or books, something that has like a high level structure and then it is made up of these atomic chunks. So you use like a summarization chain to summarize the chunks and then you vectorize the summary. So now you can search through the, at the podcast level and then search within the chunks once you have the matching podcast. Another interesting idea. So this kind of concept of summary indexing and then abstract descriptions, that's kind of like the semantic match that drew me to this paper. But they have this really interesting new connection where you use these summaries to train embedding models, and they publish these new embedding models. They make some big claims about the quality of them. We've integrated them in Weaviate, and they do look like they're pretty interesting models. So it's quite an interesting paper that actually ends up being related to these works like In Pairs, Promptigator, this kind of idea of use large language models to generate, say, queries, or in this case, descriptions that you can then use to, benchmark the performance of, say, different zero-shot embedding models or train your own embedding models. So this concept of summary indexing, I have to give a quick shout out to Jerry Liu at Llama Index. He's written a lot of great content about, this kind of idea of using these summarization chains to then represent, high-level objects based on their summaries. This is also really relevant for what we've been doing with generative feedback loops. Generative feedback loops generally describing taking data from Weaviate, sending it to an LLM, and then saving that generated data back to Weaviate so you can semantic search through the generated results. So, you write the summary and then save the summary back to Weaviate, and then you index the summary to search through the summaries. So here's a quick explanation of what they do in the paper. They use this prompt, let's write abstract descriptions of sentences, the few-shot prompting idea where you give it a sentence and an example of an abstract description. So in this case, an abstract description, it doesn't mean a summary of long text. It means a transformation of the text into the abstract thing it represents. And so we'll see an example of that in a second. Also in the prompt, you have this kind of like note, some more meta information about the task, this kind of prompting strategy. And then one other interesting thing about the prompting strategy is that you have this write 5 good and then 5 bad descriptions and then output a JSON file with the keys good, bad. This is a really interesting prompting trick that you can use to kind of get 10 generations out of one prompt, and then you index the keys, and you have things like, say, the LangChain output parser, camel case. This is like one example of how you structure these outputs to make it obey the JSON file. I mean, these language models are really surprisingly good at respecting this kind of JSON file structure, and then you can parse it and send it along the chain. So here's an example of what they mean by abstract descriptions. Say you have a sentence like, dopamine constitutes about 80% of the catecholamine content in the brain. You then transform that specific sentence into a neurotransmitter found in the brain in high concentrations, because this abstract description is probably more likely to match the query. So like, imagine a user and their information needs, they come and they're like curious about neurotransmitters in the brain. And so this kind of abstract description, it probably like vectorizes and indexes better than this specific sentence. And that's kind of the key insight. But the other key insight is that they also generate bad descriptions, and then they use this to train embedding models. So it's a really interesting generative data augmentation and then self-supervised way to train these next generation of embedding models. And they've published new embedding models. So staying on this concept quickly of how embedding models are trained, this is something at Weaviate we're always trying to stay on top of and give people the best advice of where the best text embedding models are, which vectorization models to use. So the general idea is that you want to have good negatives when you're training. So in your contrastive learning objective, you're trying to make the vector representation of this meerkat similar to the vector representation of this alternate view of a meerkat, but then not a similar vector to this picture of New York or this golden retriever. So the idea of good negatives versus bad negatives is that, contrasting the vectors of these two meerkat pictures with a dog is better for learning a semantic embedding space than contrasting it with this picture of a building. So we previously had looked at this paper from Ori Ram and his collaborators about the spider algorithm. So the spider algorithm is a way to look at overlapping n-grams between passages in Wikipedia articles. And so, like if two passages of text you have the same n-gram, like the priesthood for himself and his male descendants, that would be like a good example of a positive, and then you just use the other snippets of text in the Wikipedia page as negatives. So we're always on this hunt for how can we self-supervise, how can we automatically annotate positives and negatives at scale with web scale data, and that's kind of like where these zero-shot embedding models come from. So this paper is presenting a really interesting new way to, instead of looking at these overlapping n-grams from Wikipedia pages, you're contrasting the good descriptions with the bad descriptions. So this is the anchor, this is the positive, and this is the negative. And that helps with, the representation learning task. And, they generate quite a large scale amount of these, roughly, I think like 169,000 that they use to do this. So you can imagine, scaling this up like crazy. And it's pretty interesting. So in the end, they're going to, combine two loss functions, the triplet loss. Triplet loss is where you have, the distance between the anchor and the positive and the distance between the anchor and the negative, this kind of thing. And then you also have that in-batch negative thing. And then, you weight the two loss functions with this alpha. And then in the end, the way that they evaluate this, the state of evaluating embedding models is, you have the beer benchmark, which is a pretty solid thing, but generally it's sort of hand wavy. This is sort of the pinnacle of that. But they have a human study survey, and they do show that the humans in the study rate this model to perform better than these other baselines, like AllMPNet base 2, that's a really strong model available in Hugging Face sentence transformers, or say BM25, which is the keyword matching. So 5 is, we'll get more into the details, but basically they show the human annotators 5 search result, a mix of 5 from one of the models and 5 from another of the models, and then they rate the top 5 results. And so they're saying that they chose this one 5 most of the time, and then say BM25 was chosen like 0 out of the times of most times. So they're saying that all these models perform better than BM25 really, and that, this model is the best. Quickly, before diving further into the details of the paper, quick thank you to March Nantes for adding these models into Weaviate's text-to-vec transformers images. So if you want to run these yourself, here is the image for adding these new models. So, if you want to just stop the video now and just see what these models can do with your Weaviate example, then this is the image to do so. So thanks, Martin. So following that quick description of the paper, let's kind of walk through it a little slower. So the background is that this paper is marrying these ideas of summary indexing with this general concept of large language model generated training data for self-supervising embedding model training. So this idea of summary indexing has been one of the most powerful kind of ideas around LangChain Llama Index and these kind of LLM tools. So this article from Erica Cardin is published February 21st is, when LangChain first came out, one of the most powerful things were these summarization chains. We also, we've been building on this general concept of sequential chains, like where the name LangChain comes from, where you chain together language model calls such that the output of the first call is the input to the second call, and so on. Summarization chains have been the most interesting kind of example of this. So probably my favorite one is this refine idea. This is probably the best way to say summarize a podcast. So you take each of the clips of the podcast, and you say, write a summary, you'll receive these clips one at a time. So it writes this intermediate summary, and then it keeps taking the clips, updating that intermediate summary until eventually it's looped through all of the podcast clips and ends up with a final summary. There's also like this map re-rank and map reduce. I see these as really interesting for, say, question answering. And then I think this kind of refine idea is really interesting for summarization. There's also an idea that I think originated in Llama Index that was like this tree summarized. So you say line up all the text chunks, in a list, and then you kind of couple them in twos and build up the tree with the summary that way, and aggregate it to the top. So, but generally this concept of applying these chains to summarize content, and then you have this summary of content that you could then say vectorize and build indexes with or use. And that's kind of the question is, okay, now what do we do with the summaries? So this is also highly related to the concept of generative feedback loops that we're really heavily exploring at Weaviate. This is the general concept of where we do these retrieval augmented generations. We send specific data from Weaviate to these generative models, and then we save the resulting generation back in Weaviate to then maybe access for a future retrieval augmented generation, or in this case, semantic search through the generated results. So when we first published our blog post using Airbnb listing examples, we were taking the symbolic properties of the Airbnb, like how much it costs, how many bedrooms it has, and we took all that and we synthesized a text description of it that we would then index and search through. So it's kind of a similar concept to this summarization index, this idea of transforming data to facilitate searching through it. The next really interesting idea, and that's what that's why I think this paper is so interesting, it's kind of marrying two different schools of thought. And I love this when you had there's some connection that you hadn't originally thought of, is this idea of large language model generated data for training search models. So this is a picture from the In Pairs paper. You take a document like, we don't know a lot about the effects of caffeine during pregnancy on you and your baby, so it's best to limit the amount you get each day. So imagine you have this big collection of text chunks. It's like if you're building a text search app with Weaviate, that's probably like the situation you find yourself in. You probably don't have these questions already. So, having a query log already is more of like a big company thing to already have this kind of established thing. So what you can do is you can take the large language models and generate questions. What are the effects of caffeine during pregnancy? And this document, would say be the best answer you have. I don't know if it's like specific enough for this question, but like this would be like a way to pass this into the language model, prompt it in some way to generate queries. And now you have like query document pairs to, either say compare the embedding models. If you want to say, I don't want to use the OpenAI embedding models because it's 1536 dimensions per, vector, and then I can't afford, it's more expensive. So I want to use, say, the 384 dimensional embeddings from, say, the sentence transformer DPR models, and then, so like you want to ask these questions of which embedding model should I use, but you don't have data to benchmark. This is a really interesting solution to that, to give you data to then, understand what the difference in the models are going to be for your search app. And then also it's interesting for training custom embedding models for your data, which would also probably give you better results. So two extremely interesting things that you can do with this kind of LLM generated search data. So here's the motivation behind the novel insight. Instead of generating specific queries that match specific information, we generate these abstract representations. So for example, a lot of these information retrieval data sets and then the embedding models that are trained on them, like say they're trained on the squad, question answering data set, it asks questions like, what is the atomic number of oxygen? The answer is 8. Or like, what year did this king rule over, France for? And then it's like some specific date. So most of these data sets that have been created and, published are like query and then like specific thing that comes out of the query, rather than this kind of like abstract information need. And the authors motivate this by saying, the user is not interested in a definition or a single answer, but for sentences whose content is a specific instantiation of their query. I think that this is a great quote because it's more in line with like this kind of semantic search concept. You're looking for like, semantic matches, not like specific matches to questions in the thing. So it's interesting there. If you're interested in this kind of thing, there's also this set of embedding models called the instructor models, where they're really digging into the different information needs. And it's quite an interesting topic. But they give this example of, say you have this query, substance abuse in animals, right? Like just, this kind of abstract query. That would be a better match for the studies have shown that a subpopulation of primates chronically consume intoxicating amounts of alcohol. So it's like this kind of query compared to something like, which primate has been found to show, like, and then it would be like some specific kind of species of it, the kind of difference in what these data sets look like. So another quote from the paper, just sort of laying that out more explicitly: systems that are trained to retrieve passages that contain answers to questions, for example trained mostly on squad and data sets like this, beyond being focused on questions rather than assertions, are also focused on specific answers rather than abstract situations. So it's a bit meta, digging into thinking about information needs and information retrieval, but I think it makes a lot of sense. Usually with these kind of queries, you're like fuzzily looking for some kind of similar concept rather than the exact match to your question with the embedding model. So digging further into the paper, this is the prompt that's being used to generate these valid and invalid descriptions per sentence. So we start off with the main prompt of let's write abstract descriptions of sentences. Example. So this is kind of the structure of prompts these days is you start off with some description of the task, then you have few shot examples of what input output should look like for the task. So sometimes you can omit this, but generally, I've done a few interviews with people about, who work on like agents in production, this kind of thing. And generally the consensus seems to be right now that keeping these few shot examples of, task descriptions or say how to use a tool is still quite a productive thing to improve the performance of the language model. So you have the sentence, Pilates' role in events leading to the crucifixion lent themselves to melodrama, even tragedy, and Pilates often has a role in medieval mystery plays. So then you generate this abstract description, a description of a historical religious figure's involvement in a significant event and its later portrayal in art. So, you see how you blur out the specific, the specific details of the text, and then you instead have this abstract description of what the text is about. So then, in addition to the few shot examples, you have this kind of note to the language model on how to complete the task. Descriptions can differ in the level of abstraction, granularity, and the part of the sentence they focus on. Some descriptions need to be abstract, while others should be concrete and detailed. So then you have kind of the output prompt. So you're saying, for the following sentence, write up to 5 good and standalone independent descriptions and 5 bad descriptions, which may be related but are clearly wrong. And then here's another really interesting detail. Output a JSON file with keys good and bad. So or good comma bad, because it might even help a little bit more with the JSON file. But so this detail is quite interesting because this is this concept of, say, LangChain's recently released output parsers, camel case, like this concept of how do we make language models behave, obey the kind of API syntax to then kind of chain out the outputs and parse them with, say, just a basic kind of Python parser for how you would take this kind of output and then save each of the generations. And then this kind of idea of using one prompt to generate 10 generations this way, you can also imagine that there's some kind of cross attention across the 10 examples it's generating. So this kind of like listing out things is super interesting prompt, and then you pass it along the chain by having it follow this structured outputs. So here's the next detail of the paper that I think is extremely interesting. They're going to take the output of the main prompt and then feed it into the make more abstract prompt. So in my own experiments of generating queries for the podcast, I've also thought of doing this kind of thing where, say, you generate 5 queries, and then you have to ask it to take those queries as input and then say, is this query specific to the document? Because it'll generate some queries that aren't specific to the document. So that's kind of what I'd found in my little how I've been investigating this a little bit. So I think it's really interesting that they're formalizing this make more abstracts prompt and this kind of prompt chaining with the generative feedback loop for the LLM-generated training data. So what they do is, out of the 5 valid descriptions, they're going to take each one of them and then they're going to generate 3 more from them by feeding them into this next prompt. So remember, again, you have the JSON file. So you index the JSON file with the good keys, and then you have this new prompt. So you have the sentence description pair, and then you have a very abstract description. So again, we have this few shot example thing where we're giving the large language model an example of what we want this to look like. And then, we roll with that, where we plug in the sentence, we plug in the original sentence, we plug in the description, the valid description that was generated in the, first thing, and then we get a very abstract description. So, it's a really interesting way of kind of chaining this along and refining the output of the, curating these descriptions or summaries. So here's another really important detail of this. They do this at pretty large scale. So if you were skeptical about whether these models would be any good, with checking them out with, say, the sentence transformers library, I think this is a reason to be convinced to check them out. So, for each of 165,960 Wikipedia sentences, they generate 5 valid descriptions and 5 misleading descriptions. So, doing the math, that's roughly 800,000 of each. And then they are also going to do that and make more abstract prompt from 3 of 70,000. So for each of these 165,000 roughly Wikipedia sentences, they're going to have 5 to 8 additional pairs and then 5 misleading pairs. So the train is you have this kind of local comparison where that's the way they did the metrics. But so anyway, so it's interesting to see the scale of it, really. Doing the million of each thing and doing that kind of scale. It's a large enough scale to think that these models would be quality zero-shot embedding models. Of course, then you could imagine scaling this up further with more Wikipedia sentences, but it's pretty interesting. So quickly, before we even dive further into the human study evaluation, which is quite interesting in its own way, let's quickly touch on how embedding models are trained, just quickly in case you're not familiar with it. Basically, you have this kind of triplet loss, or you have this info NCE loss. They're going to combine both of them in multitask learning. The way that you do the triplet loss is you take, so this is the vector encoding of the anchor. This is the vector encoding of the positive, vector encoding of the negative. Whereas with the batch negative, you loop through the encodings of all the other examples in the mini batch. So, the way deep learning models are trained is you sample a batch of data points. And so with contrastive learning info NCE, you have your anchor and positive, and maybe also you would have a negative in there that you could kind of mix with this, but you could, so you have the anchor and the positive, and then just every other anchor positive pair that's in that mini batch is used as a negative, and you loop through and you take the e to the the distance, and this is how you do this kind of like differentiable loss function and scale it by doing this stuff like taking the log of it and that kind of idea. So with the triplet loss, you kind of like explicitly compare 2 points. You have the margin hyperparameter that is then plus the vector distance, so the L2 distance between the anchor and the positive vectors. Subtract that with the distance between the anchor and the negative, and then you normalize it also by having this large batch. So this kind of loss, I think just the quick commentary is like this kind of triplet loss thing, this is pretty friendly, this not too ugly to train with, whereas this kind of info NCE thing, I think this is a little more prohibitive with people training embedding models, because this is a bit more of a chaotic thing to orchestrate with how you have to have this like diagonal matrix to get the labels. So this is where I think a lot of the skill and the expertise in training deep learning models comes in, and just sort of an interesting detail if you're interested in exactly how the embedding models are optimized. So here's another pretty interesting detail of this paper. Instead of reporting the performance of their model on MS Marco, beer benchmarks, they're using a human study with mechanical Turk workers. So you begin by instructing the the workers about what the task is, and so you're shown a description in 10 sentences. You're asked to choose the 5 most relevant descriptions. So then what that ends up looking like is a period of difficulty and sorrow for an individual, and then you choose, you rank the top 5 by choosing 5 from this list to submit as which you think are the retrieved sentences that best fit this description. So in the end, you see that they chose the new abstract sim models. On the average, they would choose 3.78 out of the 5 selected sentences whenever they did a head-to-head comparison, ablating each of these 2 models against each other in tournament style combinatorics. So, you had pairs of abstract sim 5 versus all MPNet based V2 5, and that made up the 10. So each of these 2 have been compared with each other 5, in this kind of amount of times. And then you see kind of the bar chart of the performance, how many times it was chosen out of the 10, and showing that these models perform pretty well in the study. So here's some examples. If you want to go through it, you see kind of the difference in how it captures the specifics, by how it captures this kind of abstract concept with this new generation, the kind of better results that leads to some specific examples of that if you want to dive into it. So here are some final takeaways I had after reading this paper, Retrieving Text Based on Abstract Description. So firstly, I'm thinking heavily about this kind of summary index concept, and I think that what we're seeing is the cost of large language model inference is getting cheaper and cheaper, such that this will be something that's more common to do. As we're seeing all these open source models, I think Falcon being the latest one at the time of this recording, but we're probably going to see cheaper and cheaper large language model inference, such that summarizing all of your documents is more of a economically sensible thing to do based on your app or whatever you're building. So it's very interesting with this respect to custom data for your documents. So I imagine a lot of Weaviate users have just the documents rather than the queries, because you're building kind of like a new app. You don't already have all this like user data and this kind of log of queries. So now I see there's kind of 3 things that you get out of doing this LLM generated data. First, you get the summary index that you can use to kind of index the data to search through. You can also use then the original text and then these abstract descriptions, and then how well you're able to retrieve the full text based on the abstract descriptions to compare the performance of zero-shot models. And you can also use that as data to train custom search models. So kind of 3 use cases you get out of this LLM generated data. You build a summary index, you can ablate the different embedding models, and then you can maybe train your own custom models if you want to go for that. So then I think this general concept of summary indexes is super interesting for this concept of top level indexing. So if I have a whole podcast, I want to summarize the whole podcast by doing that create and refine summarization chain through each of the clips. And then once I find the podcast that matches my query, then I will search within the podcast. So I'm just generally interested in that kind of phenomenon. I don't think the paper particularly made me think more heavily about this, but I just think it's something that's very interesting. So then there was another paper that came out recently, which was Voyager, this Minecraft paper where you learn skills and then interestingly, what they did also is that they had an abstract description of the skill programs, and that's what got indexed when they were retrieving. So it's just an interesting thing of how you would summarize some kind of really abstract thing to then index the summary of the thing and vector search across summaries. I think is really interesting. So maybe something that's just like an idea is maybe we could retrieve with abstract descriptions and then apply these re-rankers like cross encoders to the original full text as an idea. And then another thing is I just think this kind of how do we judge the quality of these LLM-generated descriptions? I think this is quite an interesting topic. So with respect to this last point of how do we judge description quality, Weaviate Podcast 48, I had the pleasure of interviewing Professor Laura Dietz, and I love this paper, Perspectives on Large Language Models for Relevance Judgments. And I think it's really interesting to relate to this. So, what we previously had, human judgment, this, like let's say like the Trek benchmarks for information retrieval, like humans would just, annotate the relevance of queries or say like, we would divide up our team so everyone on our team writes 10 queries for each of our documentation or something like this in order to benchmark our search systems. Now we say have AI assistants where we use the LLM generated summary of the document. Then we have like a human filtering layer where the humans look at the output and kind of rate them. Or maybe we do just different tasks generally. I think another interesting idea is 2 LLMs each generate a judgment and a human selects the better one. So this is kind of similar to me to the make a more abstract prompt where you say take the original 5 valid descriptions and then you generate 3 more. You could also imagine an intermediate layer there where the LLM takes the 5 generated descriptions and says, you can only take 3. Which are the 3, best abstract summaries of this content? That kind of idea of chaining away with the language model. And so, it's just a really interesting, the times end thing, this whole spectrum of how we're thinking about using large language models to, annotate, say, query document pairs, relevance, or say also judge the quality of generated text. This is a problem as old as generative modeling is how do you judge the quality of generated images or generated text. And so with images, we had things like the Frichet score, inception distance for say GANs. And now with text, it's when you write a summary of, some text, how are you going to, you can't what they have now is Rouge scores, blue spelled BLEU scores, which is n-gram overlap to some human annotated gold summary of the text. So it's how are we going to be annotating this kind of abstract description? So I really enjoyed this paper, and I think this is another interesting perspective on LLM generated data that we can use for search. So one more thing before wrapping up, I'm working on a new demo of abstract description summarization indexes using the dogfooding of the Weaviate podcast transcription. So if you haven't seen this project already, please check it out and stay tuned for Generative Feedback Loops Part 2, exploring generated summaries for each of these podcast clips and the summaries of the podcast themselves, exploring writing personalized summaries of the podcast for different people, writing biographies of people based on the podcast content, and also say automatically finding chapters from the podcast by prompting it. So exploring further how we can use large language models to transform our data and then save that transformed data back into our database for some kind of future purpose. Thank you so much for watching this paper summary video of retrieving text based on abstract descriptions. Please subscribe to the channel for more content around vector search, retrieval augmented generation, approximate nearest neighbor search, and all these cool topics. Please check out Weaviate at Weaviate.io or open source on GitHub at Weaviate/Weaviate, and follow us on Twitter at Weaviate.io. Thanks again so much for watching.